Thank you. We don't know how humans navigate or the representation they use, but here are two possibilities. They might use a map or grid-like representation with coordinates, or they might use a graph where a set of neural states or images are connected by actions. And reinforcement learning is developing representations like this. So the main take-home message of my talk is that humans and animals use hierarchies of categories, including for navigation. This is an example using a single image, which you might call a blue antique jar. And that would be a very coarse category, whereas an expert might say that's a Delftware drug jar, or an even more expert view would be that this is a London Blue Delft jar from the late 17th century. So the point is here, I've used the same stimulus and a hierarchical classification according to expertise or training. Now, deep neural nets don't have a hierarchy of this sort. They can recognize blue objects in some high-dimensional space and spheres in the same space. But they don't have compositionality, so that if you try and pick out the images with blue spheres, they can't do that, or at least they need to generate a new category to be able to do that. So I'm going to talk about location represented in the same hierarchical way. And this is work done by Alex Murray, funded by the DSTL. So if you're in an environment and all you can see is mountains, then the representation that you can build, a set of angles between points, is compatible with being in many different locations. Whereas if you put in near objects like these trees, then there's a smaller range of locations compatible with that representation. And if you add even near objects like this picnic table, then you refine and define the location even more precisely. So this is not a map with coordinates. It's much more like a postal address, going from coarse to fine. So finally, I want to talk about an experiment, and here's a slide showing the conclusion, which is if you go to Ho Chi Minh City, which is notoriously difficult to navigate because it doesn't have a grid-like structure, then you could early on find a route between A and B long before you could accurately point between A and B. And that's the result we find in this experiment. So it's done in virtual reality. People are walking around with a headset in this maze, and what I want you to concentrate on is the blue and red dotted line and what happens when the observer goes through them. So you can't see this when you go through that trigger point, but as you do, the layout of the maze changes. It's called a wormhole, and we're interested in how that affects people's representation of space, particularly according to different tasks. So you saw the green object there. The green object they can only find in the wormhole, and so that has an interesting effect on where they think the green object is. So there are the two tasks: find routes between targets and point to unseen targets. And here are the results. So if they look at the results of walking, so route finding between targets, then so the definition here is walking distance relative to the shortest route, normalized to the stable maze performance. That's with no wormholes. And what you can see is the performance doesn't change very much whether you have one wormhole or three wormholes. And that's because the topological graph that describes the scene is the same for all these conditions. And the topological graph is all you need to get between one target and another. But the pointing performance is quite different. So here the definition of performance is a standard deviation of pointing errors normalized again to the stable maze performance. And there you do need something like a metric or a map type of representation in order to perform correctly. So by definition, the performance is the same there as for walking, but it gets much worse for one wormhole and even worse for 3 wormholes. Then people really don't know what's going on. So here's the location of the green target, really. But here's where people think the green target is because it's within the wormhole, and that's the only place that they can find it. So a topological graph is a bit like this coarse scale, broad category, because many different structures are compatible with the same topological graph. The metric or map-like representation can be seen as a subset of topological graphs, a labeled graph. So it's much more precise, and you need that in order to do the pointing performance. So it's not surprising that people have different performance for these 2 different tasks. So in summary, 2 things. First, we don't use a map, at least not one with coordinates. And second, instead we use a hierarchical representation and a hierarchy of strategies, and those 2 are related. And I showed you a hierarchy of strategies in there briefly in the experiment that we've just seen. So I'd like to thank particularly Alex Murray, who did both the modelling and ran the experiment, and the DSTL for funding this work. Thank you very much.